I will try to improve performance of this selective amplifier or oscillator. To that end, I first study the input stage. I have cut the connection between the J FETs here from the bipolars, the first stage bipolars, and then connected the emitters or the sources of the FETs through this big capacitor to an extra BNC connector here. On the schematic diagram, I have just cut here and connected a connector here, which I can send signals into, or I can see in both directions in this amplifier, from here to here, or backwards from here to here. It's the backwards performance that is most interesting to start with. Here is what I see on the network analyzer. The input impedance here, it is negative, minus 28 ohms. It doesn't oscillate because I am loading with the network analyzer, which is 50 ohms. The filter response that we see here, it shows a Q of 94,000. Now I am looking in the forward direction. The gain is 11.5 dB and Q is 95,000. I can increase the power and you can see the curve becomes lower, and if I look for the Q, marker, search, bandwidth, the Q is down at 77,000. This means this level is a little too high for the crystals. Or maybe there is some compression in the transistor. I cannot say for sure on this study, but I think it's the crystals. I have modified the schematic diagram like this. A bifilar core gives me here 180 degrees reversed signal from the source. And then I have a trimmer to put that into the gates, to balance out the gate source capacitance. As a result, the backwards picture is very different. The signal is very weak and the impedance on the source is now about 12 ohms. This is much better than before, although on the resonance it's a little bit higher. Let's see, measure 1 and marker. It's 20 ohms, 19.5. So I need to connect 30 ohms in series to get the 50 ohm signal source to measure the noise floor that I have at this point. The forward response is like this now, and I look for the bandwidth. The Q is 71,000, so it is a little bit lower. Gain is also lower. It looks like much lower, but that's because of the 30 ohm resistor. I have to have a matched output. I now connected a 50 ohm source to this directional coupler. That's to establish the room temp, the 0 point. And I've calibrated Linrad to show 0. And then I move that connector to the 50 ohm output from the J310 group, like that. And there was a noise increase when I had nothing collected at this point, but I wait for a while to see the temperature of the 50 ohm here, and it shows me that the noise from the junction FETs are in the order of 0.07 dB. Very small indeed. But I don't need a notch filter, I will do this without it. This is now the low noise amplifier connected directly to the noise head. And I will check the noise figure. And here I have a 3 dB increment. And that is for a noise figure of 5.3 dB. And now I connect it to the 50 ohm output from the junction FETs of the selective amplifier. Here the noise is 0.16 dB above the system noise at the noise figure of 5.3. So it's a very low excess noise. So what I found is that the excess noise due to the noise of the junction FET is minus 183 dBc per hertz. Obviously it has to be different on the resonance of the crystal. So if I click at 10 megahertz where the resonance is, and then I have to widen the display and bring down the scale here. And here you can see there are some 10 megahertz signals around, but the noise trumpet from the noise of the crystal goes like this, something. And since we are 14 dB below room temp, this curve should be at least 14 dB above the floor at 10. That makes 24. So it is roughly in agreement. We see the thermal noise of the crystal, but off resonance the crystal is a capacitor or an inductor with a low impedance, and that doesn't give any noise. That's the basic idea of getting very low sideband noise in oscillators. I now want to establish the maximum input power to this first stage in this unit. My network analyzer is faulty. I cannot set power in 1 dB steps. So I added this stepped attenuator plus 2 amplifiers, this one and that one. And then I can look with this network analyzer on the bandwidth function. And at low signal levels, Q is 70. And I bring the level up. And now it is 64. Even more signal, it's 54. So this is obviously too much. And also this, 64. And what I wanted is, this is only 10 dB less, it's about 70. So I make finer steps and look at bandwidth. $66. $67. Well, $68. Well, this could be a suitable maximum signal level to retain a good Q. Now I turn down the supply voltage. I'm running at 18 volts and I turn it down until I see a difference here. Well, frequency changes because capacitance changes with voltage. So I look at the Q. And it has gone down a little bit. So there is some compression, I think, in the transistors. And that happens already at 10 volts. So maybe the compression I see has to do with the transistors. I have to investigate that. So I decide to select this Q64000 as the signal level to aim for. I have lost in Q. Marker search bandwidth. We are at 63,300 again. So I go for power and level and -20 means a much weaker signal level. And it is clear that there is a little bit less loss and that there is a little bit higher Q. So marker, and the Q is now 70,000. So the very close in phase noise is degraded by this phenomenon, and I'm not sure whether it's the transistor group or whether it's the crystal. I think it's the crystal, but I'm not sure, and actually it doesn't matter. I just take this level and then I can analyze the performance of the unit with strong signals at a later state. The maximum level I see on the emitters, on the sources, is 6.85 volts. Take or give on the decimals, but 6.8 volts about, peak to peak. I have reconnected here and disconnected here. Note there was a drawing error I have corrected here. And then the impedance at this point is extremely low. So I put the 47 ohm resistor in series with the cable to the output connector. This has not changed the frequency response at all. Obviously, the emitter follower shouldn't change the waveform as long as it's not very heavily loaded. The noise floor is much higher now. That's the noise from the bipolar transistors. If I could have a better final transistor, I could lose less current through these ones, and that would reduce the noise contribution from them. But I don't know much about low noise transistors. What I have in my junk box is everything more than 20 years old. I have reconnected the power transistors and added some components: resistor, inductor, capacitor, inductor, diodes, capacitor, and a resistor. That is to provide an amplitude-limited signal of a suitable level to feed into the amplifier input. That converts the units to an oscillator. And I have set the power to -1.5 dB here, means 18.5 dBm. The lid is back on, and now I look at the noise floor. It's 1.4 dB, so it's much better than before. The noise figure of the test system. This is the noise floor without the noise source on, and this is with the source on. That is 8 dB. The oscillator is now running at 18.2 dBm. And the noise floor I see 50 kilohertz on the side. It's 1.6 4 dB above the noise figure of 8 dB. I have disconnected the feedback loop. That makes a very small difference, 0.15 dB from 164 to 150. It means that it is not modulation of the carrier, it's the white noise from the transistors. The noise figure 8 dB means minus 166 dBm per hertz in power. 1.64 dB above that is 1.46 times. So the noise that comes from the oscillator, the sideband noise, is 0.46 times the power that we have from the test system. So it means 3.3 dB below. So the sideband noise is minus 169 dBm per hertz, and for an 18 dB carrier that comes out as minus 187 dBc per hertz. And half of that is phase noise, so it's about minus 190 dBc per hertz. Switching off the feedback, turning it into an amplifier with no signal, the noise floor goes down by 0.14 dB only, which means that the phase noise due to the carrier, it is probably phase noise, but it could also be AM noise, I don't know for sure, that comes at minus 202 dBc per hertz at 50 kilohertz separation. So with conventional notations, B0, the phase noise is minus 190 dBc per hertz, and the B0 for AM noise is also minus 190. The B minus 1, phase noise plus AM noise, and I don't know how much of one or the other, that's at minus 155 dBc per hertz. This means that I expect the noise at 1 kilohertz to be minus 185 dBc per hertz. This is not something that I can measure today.